Hello everyone, I'm Cherry Lee from Nanjing University. In this work, we propose UHDNeRF, a new framework for novel view synthesis on the challenging ultra-high resolution real-world scenes. Previous NeRF methods are not specifically designed for rendering on extremely high resolutions, leading to blurry results with notable detail losing problem even though trained on 4K images. Here's an example. On the left side, we have a 4K image. When we zoom in on a specific area, like the remote control, we can observe that the advanced methods like instant NGP suffered from noticeable loss of details. In comparison, our method preserves details effectively. The main difficulty preventing a NeRF model to generate ultra-high resolution images is the mismatch between the high-resolution input and the low-dimensional volumetric representation, which is determined by the density of samples. For example, in the original NeRF, each ray samples around 200 points, which is too sparse for SIMs to super high resolutions, leading to skipping of high-frequency components and loss of fine-grained details. A straightforward solution is to use dense sampling. While theoretically feasible, it raises another problem. Specifically, rendering a 1K image with NeRF takes around 1 minute. In the case of 4K rendering, the computational cost increases at least 16-fold times, which means it would take at least an hour to render a single image. This is clearly unacceptable. To reduce the computational cost, some methods adopt hybrid sim representation. For instance, point NeRF combines NeRF with dense point clouds for fast rendering. However, it is challenging to reconstruct dense point clouds for high-resolution real-world scenes, specifically for the background areas, which result in holes in the render results. Taking these issues into account, we propose a method that combines NeRF with sparse point clouds. Our method employs an adaptive implicit-explicit sim representation, achieving high-resolution rendering quality. Our framework consists of two branches, a high-frequency branch and a low-frequency branch. For each sample, we adaptively assign it to one of the branches. Specifically, for an input image, we perform patch-based sampling and gather point clouds within the region. For each sample, if it lies in regions without a point cloud, we consider this sample locates in a low-frequency region and use the low-frequency branch for prediction. Otherwise, we consider the sample to be in a high-frequency region and we predict sim properties using both the sample's information and the point cloud features. To better explore the high-frequency information embedded in the sparse point cloud, we generate a global structure feature and a local point-wise feature for each sample in the high-frequency branch. Here's a qualitative comparison result. When zooming in on a specific area, our method significantly outperforms previous approaches in terms of detail preservation. The quantitative comparison also shows that our method achieves best performance among all the metrics. Here's a video demonstration. As seen, our method can generate high-quality render results. Compared to NeRF, we can preserve much more fine-grained details. This is all of my presentation. Thank you for listening.